Okay, thanks very much. Um, so the work that I'll be talking about today is collaboration with Anta Levitsky from Brown University, with Minkyu Kim from Sogan, and Minkyu is in the audience, and with Jaco van Zyl from the University of Cape Town. I've tried to be pedagogical. Please interrupt me if things don't make sense. So I'm happy if you interrupt me as I'm talking. Let me just situate you. So what are we trying to do in this talk? I'd like to look at finite n effects in the gauge theory and understand what the implications are for the dual gravity theory. So this is all about figuring out the holographic interpretation of finite n effects. Okay, so just to orient you, this is the first question I'm going to think about. So let's study the matrix quantum mechanics of a single n by n Hermitian matrix X. This model has a UN gauge symmetry, and X transforms in the adjoint of this gauge symmetry. And then a question that you might ask is, what is the complete space of gauge invariant operators? So the complete space of gauge invariant operators is generated by these generating invariants, phi k, which is trace of x to the k. They're obviously UN invariants, and they generate the whole space. What we mean by this is, if you take polynomials in the phi k's, you'll get the complete set of gauge invariant operators. Also, they act freely. And what that means is there's no equations relating the phi k's for different values of k. When you come to finite n, that changes. In particular, any 2 by 2 matrix X will satisfy this equation over here, which is known as a trace relation. The existence of such an equation is very clear. Why is that? If X is a 2 by 2 matrix, it has 2 eigenvalues. If you tell me what the trace of X is, you've told me the sum of those 2 eigenvalues. And if you tell me what the trace of X squared is, you've told me the sum of the squares of those 2 eigenvalues. So I can work out the 2 eigenvalues, and then I could work out the trace of X cubed if I wanted to. And that's exactly what this equation is doing. What it means for us is that now there is an equation relating phi 3, phi 2, and phi 1, so the phi k's no longer act freely. So you can ask, how does this modify the space of gauge invariant operators? So I'm just going to tell you the answer now. We'll talk about this in a little bit more detail. What it does is it means that now gauge invariant operators are freely generated by only n invariants. It's phi k, and you restrict k to go from 1 to n. So this is a simple problem that's been well studied, well understood. This answer you would have guessed just from the fact that the gauge invariant data inside X are its eigenvalues, and X has got n eigenvalues, so that's not surprising. What's going to be more interesting for us is that we want to generalize this to a matrix model of D matrices. So there's going to be XA, A goes from 1 to D. At n is equal to infinity, again, take the space of all single trace operators. They're free. There's no equations relating these invariants. And they generate the complete space of gauge invariant operators. In this case, too, we'll have trace relations. And the question that I want to focus on today is, how do the trace relations modify the description of the space of gauge invariant operators at finite n? And the way that we're going to answer that is that we're going to solve the complete set of trace relations in this model, and we're going to see what remains after we've solved that set of trace relations. So how am I going to do that? Well, I'm going to take a lot of inspiration from a certain counting problem that I'm going to review. Once I've reviewed that counting problem, I'll be able to tell you the statement of our result. Then, to try to convince you that this result is true, I'm going to give a careful problem statement that I'm going to solve first in the case of 1 matrices, and then, with the help of the Moulin-Weil formula, in the case of 2 and 3 matrices, and then I'm going to summarize some general lessons that we learn from doing this. Okay, so let's start with the counting problem that is going to be useful for us. I would just like to count how many polynomials can I construct using x and y, and I'm going to organize the counting by degree. So for example, if I look at degree 2, what can I make? X squared, xy, and y squared. How many polynomials are there? There's 3 of them. At degree 3, we would have a total of 4 polynomials. And the counting that I'm interested in are these numbers, this 1, 2, 3, and 4. How can I do that counting? Well, here's a trick. Take 1 over 1 minus x times 1 over 1 minus y, expand both of those factors out, and then multiply the brackets as you would usually multiply brackets. And what you notice is, in this product over here, you've generated all of the polynomials that appear on this list, and you're generating each of them with a coefficient of 1. So if I now put x is equal to y is equal to t and I sum, the degree 3 term has a coefficient of 4 because there are 4 degree 3 polynomials. So this function, this 1 over 1 minus t squared that I've obtained by setting x is equal to y is equal to t, this is called a Hilbert series. The property of the Hilbert series, if our power series expand it, the coefficient of t to the n, Cn, counts how many degree n polynomials I have. Notice that there's a product of 2 factors in the denominator, and this is related to the fact that I've got 2 generators of this ring, and that's quite clear by the way that we've derived this Hilbert series. Let's consider a very simple generalization of this. Let's now go to count the situation where we have 2 generators of degree 1, 1 of degree 2, and 1 of degree 3. So now there's a total of 4 generators. The Hilbert series denominator has a product of 4 factors. There's a 1 minus t times 1 minus t for the x1 and x2. There's a 1 minus t squared for x3 squared, 1 minus t cubed for x4 cubed. And arguing just as we did for the previous example, you can easily check that this Hilbert series is again counting the number of degree n polynomials in that coefficient Cn. All of this counting has been free counting. What that means is there's been no relation relating the generators. That's not that usual. That's the simplest kind of counting problem you can find. Usually there will be relations. So let's do an example of a counting problem where you have relations. Imagine that I wanted to count the number of spherical harmonics in d dimensions. If I'm counting degree n polynomials, that would be counting the spherical harmonics with angular momentum n. So what you've learned so far, your natural guess for the Hilbert series would be, it's just 1 over 1 minus t to the d, because I've got d generators, and each of them are degree 1. That's wrong. And the reason why it's wrong is that 1 is an angular momentum 0 state, but the sum of the squares also has angular momentum 0. So when you do the counting, you shouldn't count the sum of the squares different to 1. And more than that, 1 times any polynomial should not be counted as different to the sum of the squares times that same polynomial. So you've overcounted by counting these 2 things as different. How do you correct that? Well, that minus sign over there is correcting us to the right counting. We've got minus t squared because this constraint is degree 2. There's a single constraint, so it's a 1 times by the t squared. And the fact that they're both over this denominator tells you that I've corrected for the 1 multiplied by any polynomial and the sum of squares multiplied by any polynomial. This is also a very simple counting problem. In general, you won't just have 1 constraint. You may have many constraints. You should subtract a term for each constraint that you have. But in general, if you do that, this is where you'll make your second mistake, because all of those constraints are not independent. So when you subtract off too much. So now you have to add something back in for the relations between the constraints. But this is where you might make your second mistake, because when you add stuff back in for the relations between the constraints, not all of the relations are independent. There may be relations between the relations. So you added too much back in, so now you need to subtract something back off. And now you guessed it, you can make your third mistake because you subtract too much off, and so it goes on. The language for this is the constraints between the generators are called syzygies, the relations between the constraints, second syzygies, the relations between the constraints, third syzygies, and so on. And one of the central results in the subject is that Hilbert's syzygy theorem tells us the depth of the syzygy structure is controlled by the number of generators. It can never be bigger than the number of generators. Good news for us, all of our counting today is going to be free, so we don't have to worry about constraints at all. This is the counting problem that is going to be most relevant for us. So I'm going to change the rules slightly. I'm allowed to use x and y freely, and then I must use 1 and only 1 from that set. So I can have 1 times anything built out of x and y's, w squared times anything built out of x and y, and v cubed times anything built out of x and y. This is not a ring anymore. Now we're studying a module, and again, use the same argument that we did for our first example. If you expand out these factors and then multiply the brackets out, you'll see that we're generating the complete list of polynomials allowed by these rules, and we're generating each polynomial exactly once. So setting x is equal to y is equal to w equal to v equal to t, we obtain this function whose power series expansion is that. So let's just check one thing, make sure we know what's going on. That 7t cubed should tell us that there are 7 degree 3 polynomials. Well, let's count them. From the 1, we can have x cubed, x squared y, xy squared, and y cubed. From the w squared, we can have w squared x, w squared y, and from the v cubed, just v cubed. Well, that's a total of 7. Good. So this Hilbert series is again counting the number of degree d terms multiplying t to the d. I want you to keep something in your mind from this counting problem, and it's the following. So if we look at this Hilbert series, okay, these are the objects we were counting. We had 1 w squared and v cubed exactly once, and then the x's and the y's acted freely. We could raise them to any power. The numerator of the Hilbert series is telling us about generators that act exactly once. The denominator of the Hilbert series is telling us about generators that act freely. This is not a problem with constraints, because all of the terms that you're summing in the numerator have a plus. When you've got constraints, you've got some minuses correcting an overcount. And we're going to see Hilbert series of this type. And when you do see a Hilbert series of this type, this is how I want you to interpret it. The numerator tells you about generators that act once, the denominator about generators that act freely. Why should we worry about this counting problem? So I'm going to start off by studying matrix oscillators. And what I mean by that is I'll have one matrix oscillator for each matrix. I'll sum these different oscillators to get the total Hamiltonian, and there'll be no terms in the Hamiltonian that mix the different types of matrices. I'll calculate a partition function. So what's the partition function? Sum over states, and I weight each state by e to the minus beta energy of the state. How am I going to find these states and eigenenergies? Well, I'm going to do it as I always do it for oscillators. I'll introduce a creation operator. And then if I look at the general eigenstate will be some trace of a daggers acting on the vacuum. Here I've written it as a single trace, but the only requirement is that you have a gauge invariant state. So it could have been a double trace, triple trace, whatever complicated trace structure that you like. But what I want to stress is, for every state that you write down, you have a polynomial. So there's a one-to-one correspondence between polynomials and states. For each state, there's a polynomial. For each polynomial, there's a state. More than that, if we look at the energy of this, I'm going to subtract off the ground state energy so that my energy is just given by the number of A daggers. I'll assume my oscillator has a level spacing of 1. In that case, the energy is just given by the number of A daggers, which is the degree of the polynomial. So when I'm calculating this partition function, I'm doing a sum over states, which I can say is a sum over polynomials. And I'm weighting each state by e to the minus beta e, or equivalently, I'm weighting each polynomial by x to the n, where n is the degree of the polynomial. But summing the polynomials weighted by x to the n is exactly what the Hilbert series is. So this partition function for the matrix oscillator is just calculating a Hilbert series. So now let me tell you the answers that we get for various partition functions that we've calculated. And they all take this form. So that's the form for the partition function. And if you look at this, this is exactly the form of the last counting problem that I showed you. It's a numerator that starts as 1 plus some polynomial with only positive coefficients. All of these CIS's is an integer times by the xi divided by a product of factors. Thinking about this as a Hilbert series, we immediately know how to interpret it. Each factor in the denominator is associated to a generator that acts freely. The term 1 minus x to the j is associated with a generator that is of degree j. All of the generators associated with the denominator turn out to be single trace terms. There might be a sum of single trace terms, but they're all single trace. The generators corresponding to the numerator are the generators that act exactly once. Those are called secondary invariants. Okay, so the primary invariants act freely, the secondary invariants act at most once, and these in general can have a complicated multi-trace structure, and there'll be a sum over many multi-traces. So the complete space of gauge invariant operators in these theories is given by a direct sum Each term in the direct sum is labeled by a specific secondary invariant, and it's dressed by a product over all of the primary invariants, and you're allowed to raise the primary invariants to any non-negative integer power. And that's the structure of the space of gauge invariant operators. It's just a mathematical fact. Now, let me tell you about how we want to interpret this. Yes?
The square of the secondary to another secondary?
Okay, so.
I'm just wondering whether it's once and not twice.
Okay, good. So you're going to see examples of exactly that. So sometimes you want the operator to appear, its square and its cube, but no higher powers. Then you'll have a secondary for the square, secondary for the cube. That can happen. Yep. Good. So this is the form that our space of gauge invariant operators looks like. And if you look at this form, I'd now like to interpret this physically. Okay, so now I'm putting forward a proposal. The fact that that's the structure of the space of gauge invariant operators is a fact. You cannot argue with that. You could argue with this interpretation. The interpretation that I want to argue for is that these primary invariants that act freely, we should think about those as perturbative degrees of freedom, and we're generating a Fock space of these perturbative degrees of freedom. And each of these secondary operators, they look morally like a state or a background of the theory. And then what we're doing is we're populating each of these backgrounds with some perturbative excitations. And I will try to give you evidence for that as we proceed. Good. So that's the answer that we find for the space of gauge invariant operators. So now, let me try to show you why we claim this, how we proved it, and I'm going to start off by giving you a careful problem statement that we'll then solve. So we study matrix quantum mechanics of D in Hermitian matrices. I'm going to start off studying this Hamiltonian, trace of momentum squared plus trace of position squared, one term for each matrix, quantize them with the usual equal time commutator, both x and momentum transform in the adjoint of the gauge group. And the question that we're interested in is, what is the complete space of gauge invariant operators? And this is simply given by the trace of any product of these matrices XA. When I say what is a complete description of the space, what am I after? I'd like a set of generating invariants, and I'd like to know what is the algebraic character of these generating invariants. If I can give you invariants and tell you what their algebraic character is, then I think that I've solved this problem of how to construct the space of gauge invariant operators. Okay. So here's a warm-up. One matrix. If you've got one matrix, there's one creation operator. I've subtracted off the ground state energy, so that's what the Hamiltonian looks like. And this is the formula for the partition function. In a couple of slides' time, I'm going to tell you exactly how we generate that answer. But for now, just take it. If you think about this as a Hilbert series, it looks like we're generating a ring freely with n different generators. And the natural guess for those generators would be that phi k is equal to trace of x to the k, and k can go from 1 to n. One point I want to make now is the counting is certainly consistent with that interpretation, but we haven't proved it. I mean, the counting just suggests that. How do we prove that that's actually what's going on? To prove that, we need to solve the trace relations. So now I'd like to say just a little bit about the trace relations. Where do they come from in general for a general n by n matrix? And yeah, so the trace relations are the central player of today's talk. So how do we generate the trace relations? So let's think about the simplest case first of all, which is 2 by 2 matrices. The trace relations for 2 by 2 matrix have 2 plus 1 factorial, so 3 factorial, so 6 terms. And the 6 terms are obtained like this. W1, W2, W3 are 2 by 2 matrices. So I've written down the 3 matrices side by side there. And now what I do is I anti-symmetrize on the indices I1, I2, I3. So for example, I could swap I1 and I2. So that's what I've done in this term. It cost me a minus. Or I could have swapped I2 and I3, or I1 and I3. So these are just cases where I swap a single index. In this term over here, I first swap the column indices of 1 and 2, and then I swap the column indices of 2 and 3. And in this term, I first swap the column indices of 2 and 3, and then the column indices of 1 and 2. When doing 2 swaps, there's 2 minuses, so that's weighted with a plus. So I got these 6 terms by anti-symmetrizing on the column indices. So I've anti-symmetrized 3 indices, and each index takes a total of 2 values. Well, that is always going to give me 0. So that's why this equation is equal to naught. What are these three 2x2 matrices? Well, I could construct them using a single matrix, and then Procesi in 1975 in his study of invariant rings proved that if I take W1, W2, W3 to be any matrix constructed out of the matrix X, this will generate the complete set of trace relations for a single matrix model. If I take W1, W2, and W3 to be any word constructed from D matrices, Procesi proved this will give the complete set of trace relations for a D matrix model. To lift this to n is very, very simple. All that we do is, for n by n matrices, we now pick n plus 1 n by n matrices. We again anti-symmetrize on the column index. We've anti-symmetrized n plus 1 indices that each take n terms, so this again vanishes. Taking all of the w's to be built from a single matrix gives me the full set of trace relations for a single matrix model. Taking the w's to be built from D matrices gives me the complete set of trace relations for a D matrix model. So a few things that I want you to bear in mind. The trace relations would be equally applicable if I had some fermionic matrices. So nothing here told me that these matrices were not Grassmann, so they could well have been Grassmann. I didn't use here any details about the potential or coupling strengths. So something proved with the trace relation holds regardless of what potential you've got and regardless of what coupling strengths you've got. There's only one parameter that's important for the trace relation, and that's n. So as soon as you tell me what n is, I know what the trace relations are. That's the only parameter that's important as far as the trace relations go. Okay, so now let's come back to a single matrix and let's see why this truncates the number of invariants to be at most n. And I'm again going to go back to two matrices. So for two matrices, there's our sum of 6 terms that sum to 0. If I put W1 to be x to the k and W2 and W3 just to be x, this is the equation that I get relating my invariants. If I plug k is equal to 1 into this equation, I learn what is phi 3 in terms of phi 1 and phi 2. If I plug k is equal to 2 in this equation, that's the result I get. And using my previous result for phi 3, I get phi 4 as a function of phi 1 and phi 2. And you can just go ahead and write phi k with k greater than or equal to 3 in terms of phi 1 and phi 2 using the trace relations. And now you have a completely rigorous proof that all of the phi k's with k greater than or equal to 3 can be written in terms of phi 1 and phi 2. Phi 1 and phi 2 themselves are free. There's no relation between them. So the entire space of gauge invariant operators is now generated using only phi 1 and phi 2. This was proved using only the trace relation, so this is true for any potential and any coupling strengths. And that's the proof that has to come after the counting from the partition function. So you need that proof to actually claim something. This is going to be the structure of what we'll do. We'll use the partition function to count and suggest a set of invariants, and then we'll use the trace relations to really show that those invariants span all of loop space. Okay. For multi-matrices, we're going to need to use the Moline-Weil formula. So the Moline-Weil formula is just the way to calculate the partition function. So let's go through this. So how would you calculate the partition function? Well, you have the Boltzmann weight times the number of states. The Boltzmann weight is e to the minus beta times the energy. Just for transparency in this formula, let's imagine that the A1 dagger oscillator has spacings E1, the A2 dagger oscillator has spacings E2, and so on. And now let's consider a state constructed by applying N1 A1 daggers to the vacuum, N2 A2 daggers, all the way up to ND AD daggers. So the energy that the A1 daggers add to the state would be N1 E1, and this x to the N1 E1 is the contribution to the Boltzmann factor from the A1 daggers. This x to the N2 E2 would be the contribution to the Boltzmann factor from the A2 daggers, and so on, all the way up to AD dagger. We still need to multiply this by the number of states, which means the number of singlets you can produce by acting with N1 A1 daggers, N2 A2 daggers, and all the way up to ND AD daggers. So how do we do that? Well, the simplest way to work out how many singlets there are is to figure out what representation this state belongs to. Then we can take the character of this representation, multiply by the character of the singlet, which is just 1, and integrate over the group. And just by normal character arguments, that'll tell us how many times the singlet appears in this representation. So what is the representation of the state? Well, the A1 daggers are all in the adjoint. They're bosons, so you can swap them. So the A1 daggers are in the symmetric product of N1 copies of the adjoint. The A2 daggers are in the symmetric product of N2 copies of the adjoint, all the way up to the AD daggers, which are on the symmetric product of N2 copies of the adjoint. And then to get the total representation of the state, just take the tensor product of these different representations. So that's the representation of the state. What's the character? Well, the character of a tensor product is the product of the characters. So this product over I now tells me the character of that state sitting over there. I multiply by the character of the singlet, which is just 1, and integrate over the group. So now I've got a new formula for my partition function. To integrate over the set of unitary matrices, the first thing that you notice is this character depends only on the eigenvalues. So the integrand that we're integrating depends only on the eigenvalues of u. So we can immediately do the integral over the angles. We're left with an integral over the eigenvalues. One of those integrals is trivial. So we're left with an integral over n-1 eigenvalues. The eigenvalues of a unitary matrix lives on the unit circle. So we're left with n-1 integrals over unit circles on the complex plane. If I pick a value of d and a value for n, the integrand is completely explicit. And all I'm doing is evaluating a bunch of integrals that I can do with the residue theorem. So if you pick a value of d, a value of n, you can really work out exactly what the partition function is. So let's now apply the Moline-Weil formula. So we'll go again, n is equal to 2. We'll take a matrix x1 and a matrix x2. So now we're looking at a 2-matrix model at n is equal to 2. We'll call x1 to be x, x2 to be y. I'll introduce a chemical potential for those two matrices so that my partition function will now be a function of little x and little y. If you look at that partition function, you'd say, this is a freely generated ring with 5 generators. And it's easy to write down what those generators are because of the grading. X, for example, is trace x, xy is trace xy, and so on. But it's very easy to write down all 5 generators. Notice one thing. This is the trace of all possible single matrices or all possible products of 2 matrices. So those have been included amongst our generating invariants. What I now want to do is prove that these 5 invariants generate the entire loop space. And what am I allowed to use? The trace relations. What do I have to do to tell you a trace relation? Well, it's the sum of these 6 terms. I just have to tell you what are these 3 matrices, A, B, and C. They're all 2 by 2 matrices. And I'm going to use the trace relation, this equation over here equal to 0, to prove that with these 5 invariants, I can generate every single gauge invariant operator. So let's start off with 3 matrices inside the trace. If I've got 3 matrices inside the trace, I'll say that n of them are x, m of them are y, and m plus n will be equal to 3. For each choice of m and n, there's a single gauge invariant operator you can construct and a single trace relation you can obtain. And the trace relation that you obtain determines that gauge invariant operator. So here's an example. With m is 2 and n is 1, the only gauge invariant operator you can construct is trace of x, y squared. The trace relation, this is the only independent trace relation, is when you set a equal to x, b equal to y, c equal to y. That's what the trace relation is. You'll notice that these first terms are all traces of a product of 1 or 2 at most matrices. So these first terms are all members of our generating set. And just identifying these with their name in our generating set, the trace of xy squared is that polynomial in our generating invariants. In the same way, just swapping x and y, trace xy squared is that polynomial in the generating invariants. For the trace of x cubed, use the single matrix trace relation to learn the trace of x cubed is that polynomial, and the trace of y cubed, again, a single matrix trace relation, is just that polynomial. So for n is equal to 3, just straightforwardly with the trace relations, we can see that all possible gauge invariant operators can be expressed in terms of our generating set. Now let's go to 4 matrices inside the trace. So here something new happens. And it happens when you say, let's build it out of 2 x's and 2 y's. And it's because there's 2 distinct gauge invariant operators that you can construct. You can get the trace of x squared, y squared, or the trace of xy, xy. So now there's 2 different gauge invariant operators. Fortunately for us, there's 2 independent trace relations. So if you pick a to be x squared, b to be x, c to be x, the trace relation determines trace of x squared, y squared. If you choose a to be xy, b to be x, and c to be y, the trace relation determines the trace of x, y, x, y. And the remaining operators that I didn't discuss here, they're just like the length 3. There's a single operator and a single independent trace relation. So that's very straightforward. But here we see, well, there's something to check. Does the growth in the number of independent operators, is it always matched by the growth of additional trace relations? And if it isn't, then in fact, our claim that these generating invariants generate everything would go wrong. Okay, so we can prove that in fact it is matched, and we do it as follows. We do it by induction. So this is going to be my induction hypothesis. Single trace operators containing at most k matrices are determined by a generating set using the trace relations. So we'll assume that. And we can take k to be less than or equal to 4. What do we want to prove? We want to prove that all single trace operators containing k plus 1 matrices in the trace are determined by a generating set using trace relations. I'm going to go through the details of this. And the reason for that is this shows you how all of our results was proved. It's a version of this, just with more matrices or higher n. So let's start off and we can consider this gauge invariant operator. Trace of x to the n1, y to the m1, n1 plus m1 is equal to k plus 1. This is not the most general gauge invariant operator. It's just the one I'm starting with. n1 plus m1 is k plus 1. I'm choosing k to be bigger than or equal to 4. So n1 plus m1 is at least 5. They are both not negative, which means at least one of these two integers must be bigger than 1. Let's assume it's n1. Then if I pick a to be x, b to be x to the n1 minus 1, this is a positive power because n1 is bigger than 1, and c to be y to the m1, I get this trace relation sitting over here. Now notice that the last 4 terms in this trace relation have got double traces or triple traces, and that means that every single trace can contain at most k or fewer matrices. So the last 4 terms by the induction hypothesis can be written as polynomials in our generating invariants, and that proves that we can write the first term in terms as a polynomial in our generating invariants. So for this operator, we found the trace relation that does the job. Now let's go to the most general gauge invariant operator. And the most general gauge invariant operator takes this form: trace of x to a power, y to a power, x to a power, y to a power, and so on. So we've got blocks of x, y powers, the red block, blue block, all the way up to the teal block. If there are q of these blocks of x, y powers, I'm going to call that a type q invariant. In that language, the example that we studied on the previous slide, the example that we studied on this slide is a type 1 invariant. Okay? So for a type q invariant, I'm now going to pick a to be x to the n1, b to be y to the m1, and c to be the rest of the operator. Write down the trace relation. These 2 lines of the trace relations are all double trace or triple trace terms. That means that these 2 lines of the trace relation have at most k matrices inside the trace. The first term is a type q invariant, and the second term, because n1 and n2 got together and m1 and mq got together, is a type q minus 1 invariant. So these 2 lines are written as polynomials in the generating invariants. If I could work out the type q minus 1 invariant, I could work out the type q invariant. But remember, I know how to write down the type 1 invariant. I already worked that out. So because I know how to work out the type 1, I know how to work out the type 2. But because I know how to work out the type 2, I know how to work out the type 3. So in fact, all gauge invariant operators in this 2-matrix model can be written in terms of our generating set. And we prove that, again, using the trace relations. Okay, one more example. So one really important point, let me just stress this again. So our argument that the Hilbert series computes a partition function is only for the oscillator, because to make that argument, we use the spectrum of the oscillator. That's when we said we were counting by degree. But this second argument, where we prove that the generating invariants span the space of gauge invariant operators, that's used only the trace relations. That means that that statement, that those 5 invariant operators generate the entire space of gauge invariant operators, holds for any potential, any coupling strengths. So it's a very general statement. Okay, one last example. So now I'm going to study 3 matrices at n is equal to 2. Yes?
So, am I supposed to count the matrix and
Okay, So I am constructing the gauge invariant, say, on some time slice. So I'll be taking traces of products of the x's. You could also start to stick pi's in there. That more complicated problem I haven't studied. Yeah.
So this is like a configuration space.
Yes, exactly. Right. Okay. So here I've got three matrices. I've called them X, Y, and Z. I've introduced a chemical potential for each. That's what the Hilbert series looks like. You can immediately read off there's 9 primary invariants. It's easy to guess what they are based on the grading. But what's interesting in this example is we now have a non-trivial secondary invariant. And remember that the secondary invariant should appear at most linearly. So why do we have S appearing but not S squared appearing? That's what we're going to learn from this example. And the answer, as usual, is given by the trace relations. You see, there's a trace relation, so you have to do a little bit of work to prove this. But this equation sitting over here is a consequence of the trace relations. And what it tells you is, if you look at the operator created by S squared, it can also be created by terms linear in S and just in the primary invariants. So what that means is you never need to use S squared. All of your gauge invariant operators are already generated by acting linearly in S and together with the primaries. So why don't we include S squared? The trace relation tells us it would be redundant to include S squared as an independent operator. Good. Okay, so what is the space of gauge invariant operators? Well, it's these 9 primaries raised to any non-negative integer power times 1, or union of the set of these 9 primaries raised to any non-negative integer power times S. Using the trace relations, you can again prove every single operator in that 3-matrix model can be expressed, is one of these operators. Okay, so those generators that I showed you, the 9 primaries and the 1 secondary, generate the entire space. Here, we would say this is something like a Fock space over the trivial vacuum. This looks like something like a Fock space over some non-trivial state S. Okay, so before I go into developing the interpretation for the primaries and secondaries, I just want to make a comment about how general this structure is. So what we've been using here is the fact that our partition functions take this form. In fact, this is the Hilbert series for the invariant ring CND of GLN invariants of D n by n matrices. So mathematicians have studied the problem where you take D matrices, GLN acts by conjugation, and then you ask what's the complete set of invariants. They've calculated the Hilbert series. The Hilbert series takes that form. What's more, there's a structure of a Hironaka decomposition. Actually, there are Hilbert series that take this form, and the interpretation that I told you that the top line is just secondary invariants and the bottom line is just primary invariants, that interpretation doesn't hold. So it's not good enough to count and get this form. You actually need this extra structure of the Hironaka decomposition. And the Hironaka decomposition tells you that the denominator encodes primary invariants and the numerator encodes secondary invariants. And that's where this language comes from. For these rings, we know exactly how many primary invariants there are. If you're talking about a D matrix model of n by n matrices, the number of primary invariants is D minus 1 times n squared plus 1. This number is called the Krull dimension of the ring or the algebra. The Krull dimension is the maximum number of elements that are algebraically independent. So think about our ring that we built from X and Y. X and Y are algebraically independent. You can't express them in terms of each other. But anything else, X squared Y, well, that can be generated from X and Y. So the maximum number of generators from that ring built from X and Y that are algebraically independent is 2. It's just X and Y themselves. That ring would have a Krull dimension of 2. So this number is just the Krull dimension of the ring, the number of primaries. There's a second way to measure the dimension of a ring or an algebra. And it's given by the depth of the ring or the depth of the algebra. And what that is, that's the maximum number of equations, independent conditions that you can impose. And here's the idea. It's very natural. So we're here in a 3-dimensional room. Let's say, first of all, I impose an equation z is equal to 1. Now I'm on the surface of the table. Then I'll impose the equation y is equal to 1. Now I'm on some line on the surface of the table. And then finally, I'll impose the equation x is equal to 1. Now I've picked a point on the line, and there's no more conditions I can impose. I've actually now fixed the point. So the number of equations I can pose, 3, matches the dimensionality that I'm in. This is the idea for the depth of the ring. How many equations can you impose that are independent? Rings for which the depth, so the number of equations you can pose that are independent, equals the Krull dimension are particularly nice rings. They're called Cohen-Macaulay rings. It could be a Cohen-Macaulay ring, a Cohen-Macaulay algebra, Cohen-Macaulay module. Just as soon as the depth equals the Krull dimension, that's the statement. Why are Cohen-Macaulay algebras so nice? If you have a free algebra, that's the simplest kind of an algebra you can have. There's no relations between the generators. Every free algebra is Cohen-Macaulay. Not every Cohen-Macaulay algebra is free. So the Cohen-Macaulay algebras are, the biggest extension of the free algebras, so that this bigger set shares all of the nice properties that a free algebra has. So that's why the Cohen-Macaulay algebras are nice. What's one of the nice properties, the one that we like, it's the fact that it admits a Hironaka decomposition. So if you've got a Cohen-Macaulay algebra, you know that it will admit a Hironaka decomposition. There's a very famous theorem called the Rochester-Roberts theorem. And what Rochester-Roberts theorem proves is if you study the algebra of invariance of a linearly reductive group, you are guaranteed that that algebra is Cohen-Macaulay. If you want to check if a group is linearly reductive, take any finite dimensional representation and check, is it completely reducible? So for all of the groups that we like in physics, UN, SUN, SPN, SON, those are all linearly reductive. So the story that I'm telling you today is a very general story. It would hold for all of these matrix models and all of those different gauge groups. This is a very general statement about the structure of the space of invariance. Now let's start to develop a little bit the interpretation of the primary and secondary invariants. So how many primary invariants do we have? Well, it's d minus 1 times n squared plus 1. But one of the things that we know is if we take traces of matrices where there are n or fewer matrices inside the trace, those must all be included amongst our generating invariants because they're shorter than n plus 1. So trace relations couldn't determine them. So they must all be included amongst our set. And a natural thing to ask is, these single trace operators with less than or equal to n matrices, are they included as primary invariants or are they included as secondary invariants? To get an idea, let's count how many single trace operators there are with less than or equal to n matrices inside the trace. That's not a trivial counting problem. A much simpler counting problem is just to count the number of words of length L. So for a word of length L, you take a product of L matrices. The first could be any one of L, second any one of L, last any one of L. So the number of words of length L is just the number of species of matrices raised to the power of L. This is not really related to the trace, the count of single trace operators, because, so for example, here I've given an example of a single trace operator, which is obtained by tracing any 4 of those words. For this single trace operator, you could trace any 2 of those words, and for this single trace operator, there's a unique word that you can trace. So counting words is not the same as counting the single trace gauge invariance. But what you do know is for a single trace operator of length L, there's at most L words that when you trace it, it'll give you that single trace operator. So let's suppose a formula that systematically undercounts the number of single trace operators. I'll just imagine for every single trace operator, there are L words that give you that single trace operator. So I'll take d to the L, the number of words, and just divide by L for cyclicity. Certainly for large L, this 1 over L correction, this minus log L, is subleading. So this formula actually very quickly becomes accurate as L increases. What it tells you is the number of gauge invariant operators grows exponentially with L. So the number of gauge invariant operators will grow exponentially with n. However, only order n squared of them could be primary invariants. So that means most of these single trace operators that you need to include as primary or secondary invariants, most of them you have to include as secondary invariants. And I'll come back to comment on this a bit later. So some of these are traces of very short operators, but they must be included as secondary invariants, the vast majority of them. Here's an example. A 2-matrix model n is equal to 20. Just using polar counting, you can count the number of single trace operators that are less than or equal to n. There's 111,321 of them. What is n squared plus 1? It's only 401. So less than 0.5% of those invariants would be included as primaries. More than 99.5% of those would be included as secondary invariants. And we'll come back to interpret that. Okay, now what about the number of secondary invariants? How does that grow? In fact, mathematicians don't have a formula for that, and that's a much more complicated question. I'm going to study a two-matrix model. So this is all for two matrices. I'm just going to calculate the Moline-Weil function as a function of n, going as high as I can. And I could go from 2 to 7. If you look at the number of primaries, n squared plus 1, 2 squared plus 1 is 5, 7 squared plus 1 is 50. So going from n is 2 to 7, the number of primaries climbs from 5 to 50, and it climbs, relatively slowly. Now look at the number of secondaries. 1, 2, 64, 15,000, 312 million, 21,000 billion. So that growth in the number of secondaries is far more rapid than a power. If you just try to fit some function to those data points, you find it's growing like the exponential of an order 1 number times n squared. So that's what you would guess if you just eyeball the data and try to put a curve through it. Can you give a rigorous proof for how the number of secondaries grows? Yes, you can. And you can do it as follows. So we said before that the eigenstates of the oscillator are some polynomials on the vacuum. You can be a little bit more precise. You can write down exactly what those polynomials are. They are restricted Schur polynomials. And I'm not going to tell you too much about restricted Schurs, just what we need. If you take a restricted Schur built from NA1 daggers and MA2 daggers, we know the energy is n plus m. If you look at the labels of the restricted Schurs, capital R, and little s are three Young diagrams. R has n plus m boxes, little r has n boxes, little s has m boxes, and alpha and beta are multiplicity labels. So if you keep capital R, and little s fixed, you've frozen the energy. So the number of states with that energy is the number of values that these multiplicity labels take. So the number of states that you would have of a given energy is the square of the Littlewood-Richardson coefficient. The reason why I'm introducing that is that in 2019, mathematicians have worked out what is the biggest Littlewood-Richardson coefficient. And if we take n, m, and n plus m to be some order 1 number times n squared, and we take n to be very large, the biggest Littlewood-Richardson number is e to the alpha n squared over 2 log 2. Taking this biggest Littlewood-Richardson number, plugging it into the partition function, so estimating the partition function by just this biggest term, we can lower bound the coefficient of x to the alpha n squared inside the partition function by e to the alpha n squared log 2. So now we've lower bounded the coefficient of x to the alpha n squared in the series expansion of the partition function. But if you remember, the partition function was, there was a numerator coming from the secondaries and a contribution coming from the primaries. I now want to focus on the contribution that comes from the primary invariants and just ask, how much could the primary invariants contribute to the coefficient of x to the alpha n squared? Now, that's a hard calculation to do because we don't know the spectrum of primaries in general. So we're going to invent a second problem that is much easier to do the estimate for. And we know that the answer for the second problem will be an upper bound for the first problem. So what is this x to the alpha n squared? That coefficient there is an integer. What is it counting? If you want to get x to the alpha n squared, you might get it by taking a product of 200 x's, 100 x squareds, and 15 x cubes. So you can build this big power in terms of those little powers in a number of different ways. And this integer is just counting how many different ways you can build this big power from the little powers. If I decrease the little powers, well, there's a lot more ways to build some big power if I've got lots of little powers. So what I'm going to do for the second problem, which is simpler, I'm going to pick a k, and I'm going to say all of the xj's, which are k minus 1 or less, I'm going to replace them all by 1, just an x. And all of the ones, x to the k, and all higher powers, I'm just going to replace by x to the k. So if I now work out what's the coefficient of x to the alpha n squared in this problem, this will strictly be larger than that. It'll always be larger. And ck I can work out explicitly if I pick k is equal to 5 or 6. I'm just asking how many single trace operators are there with a length less than 5 or less than 6. So I can easily calculate that number. So if I just go ahead for this partition function and work out what is d hat alpha n squared, the coefficient, that's the answer that I get for the coefficient. So putting these results together, so our partition function is the contribution from the primaries multiplied by the contribution from the secondaries. We have lower bounded the coefficient of x to the alpha n squared inside the partition function in the full partition function, and we have upper bounded the contribution coming from the primary invariance. Here I've chosen k to be equal to 5. And it turns out that for all values of alpha, this is always less than log 2. So the primary invariance cannot supply a big enough contribution to explain the coefficient of x to the alpha n squared. What are you off by? You're off by some number times n squared. The reason why we can't estimate this number c very accurately is that this lower bound is actually quite strict, but this upper bound is very, very weak. The contribution from the primaries is much, much less than that. You can see if you just keep increasing k, this was k is equal to 5. If you keep increasing k, this number just keeps getting smaller and smaller, and the contribution from the primaries might not even be going as e to the n squared if you went high enough. But what this does tell you is the number of secondaries must grow like e to an order 1 number times n squared. If that's how fast the secondaries grow, the only way you can get that many operators is if almost all secondaries have a length of order n squared. That's the only way that you can get that many secondaries. Operators that have a length of order n squared, think about the LLM geometries, those correspond to operators with a dimension of order n squared. Well, those operators are heavy enough that they back react and they really do generate a new space-time geometry. So almost all of the secondaries will be very heavy operators that are dual to new space-time geometries. If you are studying a matrix model, like say the BMN matrix model, which we know has got a black hole in its dual, then we would conjecture that the natural candidate for those microstates are these secondary invariants. And if you just count the number of secondary invariants and take the log to estimate an entropy, this comes out to c to the 1 over n squared, which is the right size to explain a black hole entropy. So that might be very weak evidence, but at least there's the correct number of states to match the microstates. Another thing that happens, so Chi-Ming was telling us about black holes, for example, in 1/16th BPS black holes, that at a given value of n, you've got an operator that qualifies as a 1/16th BPS black hole microstate, but at larger values of n, they no longer qualify as a 1/16th BPS black hole microstate. So this is an example of a fortuitous operator, where it's really a black hole microstate at one value of n, but not at higher values of n. Here too, we can pick an operator that at one value of n at secondary, and if you increase the value of n, its character can change. It might disappear and not be an invariant at all, or it might become primary. So this looks very much like some sort of a bosonic analog of what you see in these 1/16th settings. We would also expect some of these secondary operators to correspond to solitons, something like, say, a giant graviton. These secondaries should have a dimension of order n. We don't have any supporting evidence for that. That's just something that we expect to happen. And now let me return to these secondary operators that are really very small. So things that have a dimension of order 1, but are still secondaries. So if you just go ahead and work out what these secondaries are for some specific examples, you can compute them. Amongst those secondaries, there are some that are irreducible secondaries. We call them irreducible secondaries. They are given by single trace operators. So there really are some single trace operators that appear. But then there are also some reducible secondaries that are given by powers of these irreducible secondaries raised to some power. So how should we think about that? When ADS-CFT was first proposed, one of the first checks that was done is that the spectrum of single trace chiral primary operators was compared to the spectrum of supergravity. And each single trace chiral primary operator corresponds to some kk graviton. And part of this dictionary is that the number of traces that you had in your complicated operator mapped to the number of particles that you had in the holographic dual. Now, at n is equal to infinity, the space of gauge invariant operators is freely generated. That means that you can raise all of these single trace operators to any power, so you can have arbitrarily high occupation numbers in every single graviton state. Here, in fact, we're not saying how we raise the powers of most of these operators. Most of them are dictated to us by the form of the secondary operators. And there is some highest occupation number for each Kaluza-Klein graviton state, and then you find no secondaries with a higher occupation number than that. So the occupation numbers are cut off. Why are they cut off? Because if you raised these single trace operators to a higher power, it's like taking a product of secondary operators, and we're told that that's redundant. So if you go to higher than some occupation number in some of these KK graviton states, it turns out that those are redundant with states that you have. So you see quite explicitly a redundancy between states in the Fock space of the gravity, and you see that there's an enormous reduction in the number of UV degrees of freedom that you have. So it would be really interesting to explore what implications this has for the finiteness of the holographic door. Okay, so let me just summarize. So the space of gauge invariant operators that can be constructed in these multi-matrix quantum mechanics takes the form of this direct sum. Each term in the direct sum is labeled by a specific secondary operator. It's dressed by a product over all of the primaries raised to any arbitrary non-negative integer powers. We know the number of primaries is d minus 1 n squared plus 1. They generate a natural Fock space structure. You can raise the primaries to any power you like. The number of secondaries grows like e to the alpha n squared. So these seem to be natural candidates for black hole microstates, but they are represented as secondary invariants. As n is increased, the character of invariance changes. So something that is secondary might fail to be an invariant or may become primary. This looks like a bosonic analog of fortuity. And then finally, almost all of the oscillators that would be present in the infrared, if you just look at the single trace operators, at n is equal to infinity, all of those look like Fock space oscillators. At finite n, those occupation numbers of those different graviton states are limited. So this implies a huge truncation in the number of degrees of freedom in the UV, and it's all being forced on you by the trace relations. And thanks for your attention.
Thank you for the very clear talk. Are there any questions?
So in this game, sometimes one is sort of interested in operators which are like trace x to the power I times k, like with an imaginary thing. Can the limit that, for example, for a single matrix, you have just n such operators, be translated to some bound of that number k?
So for small operators that you raise to some power, yes, you absolutely can translate to a bound. So,
even though that power is an imaginary number?
Oh, that bound for us is always some real integer. Yeah.
So about this interesting property that the operator can be classified as primary and secondary, do you know any bulk interpretation of this?
Not really. So there are very short operators. There are very heavy operators that can be secondaries. Primaries are all sort of light in the sense that the heaviest primary seems to be of order n. Those are the ones that act freely, but I would say we don't have a clear interpretation yet. Yeah.
Okay.
Any other questions? If not, let's thank Robert again.